Okay, this is the notes for section 4.6 in our book on inequalities in one triangle. To start you off, got a question for you. Where do you buy a ruler that's 3 feet long? And hopefully your answer is at a yard sale. Okay. So here's a property. If A equals B plus C and C is greater than 0, then A is going to be greater than B. So if you come up with some examples here, just plug in some numbers. We know that, well, let's say x is equal to 5 plus 4. So if x is equal to 5 plus 4, then x is 9. And we can say, well, we know that x has got to be bigger than 5. Right? And that's what this inequality is saying. It's something that should be pretty obvious. Plug in some numbers, and it's just a statement that we're going to need for the next corollary. This corollary is a corollary to the triangle exterior angle theorem. The triangle exterior angle theorem, let me remind you what that says, that if you have an exterior angle like this angle 1 here, that it's equal to the sum of the two remote interior angles. So this is not what we're looking at now, but what we have seen in the past is that the measure of angle 1 is equal to the measure of angle 2 plus the measure of angle 3. That's the triangle exterior angle theorem. And so this is like what we had in the previous property, where A is equal to B plus C. And so using the same logic here, well, then we can say that measure of angle 1 is going to be greater than measure of angle 2. Also, we can say measure of angle 1 is greater than measure of angle 3. So this is just a something that we might be able to use, and it's the corollary to the triangle exterior angle theorem. So here's an example asking why is measure of angle 5 greater than the measure of angle C? Well, the measure of angle 5, that's an exterior angle, and the measure of angle 3, angle C, is a remote interior angle. And we know that the measure of angle 5 is equal to the measure of angle C plus the measure of angle 3 by the exterior angle theorem. And if we want to use this corollary to the triangle exterior angle theorem, we get that the measure of angle 5 is greater than the measure of angle C. So by the corollary, to the triangle exterior angle theorem. Theorem 33. If two sides of a triangle are not congruent, then the larger angle lies opposite the larger side. Okay, so here we're saying xz is greater than xy. So the length of xz, let me put in some numbers here. Say the length of xz is 100, and that's greater than the length of xy. Let's say that's 80. Then the angle across from 100, which would be angle y, has got to be bigger than the measure of the angle across from the 80, which would be measure of angle z. That's what it's stated. Let me show you an example of this. So here I have a triangle, and I have the side lengths put out here and the angle measurements. And so we could see the smallest side length is 4.08. That's angle B, and that's side length of AC, and the angle across from that would be 19.86 degrees. And you see that that's the smallest of the angles. So the smallest of the angles is across from the smallest side. I'm going to adjust it a little bit more. The longest side here in this triangle now is side AB with 11.81, and the angle across from that should be the largest angle. Let's see here. It's 129 degrees, roughly almost 130 degrees. So largest angle across from the largest side, smallest angle across from the smallest side, 19.82 degrees across from the 5.22. And then the medium-sized angle across from the medium-sized side. Okay, so that's an important property that we want to know. So let's look at example 2. Here we're going to list the angles in order from smallest to largest. Well, the largest side length is 5.8, and that is across from angle K. So that's the largest angle. The smallest side length is 2.7, and that's going to be across from your smallest angle. So if we're listing this from smallest to largest, the smallest angle is going to be angle M. The largest angle is going to be angle K. And in between we're going to have angle L. Here's another theorem. If two angles of a triangle are not congruent, then the longer side lies opposite the larger angle. So this is just the opposite of the last theorem. Okay, so the previous theorem we were talking about two side lengths. We compared two side lengths. They're opposite larger and smaller angles. Here we're looking at two angles and saying, well, if we can compare two angles, then the same is true about the opposite sides. So in figure below, the measure of angle S is 24 degrees. The measure of angle O is 130 degrees. Which side is the shortest side? Explain your reasoning. Well, we're missing one angle, so before we answer, let's find our missing angle. So the measure of angle X plus 24 plus 130 is 180 degrees, because the sum of the three interior angles add up to 180 degrees. So the measure of angle X plus 154 is 180. Subtract 154 from both sides, and we get the measure of angle X is 26 degrees. So we know S is the smallest angle, and the smallest angle is opposite the smallest side. So angle S is opposite side OX. And so the shortest side is OX, since it is opposite the smallest angle. Next we have the triangle inequality theorem. So the sum of the lengths of any two sides of a triangle is greater than the length of the third side. Okay. This can help you determine, given some lengths, if you could make a triangle or not. So in example 4, we're asked if a triangle, on part A, can a triangle have sides with the given lengths 2 meters, 6 meters, and 9 meters? And then explain. So in GeoGebra, I've created segments with side lengths 2, or length 2, 6, and 9, and so I'm going to try to make a triangle with the given lengths. And so I'm going to put, let's see here, slant this a little bit. And so I've connected two of the segments, and I'm going to try to get this third segment. I can't change the lengths, and so it's a little too short there. Well, maybe if I bring this down a little bit, still not. Yeah, let's move this over here. So there's something wrong here, right? There's no way to connect these lengths because that 1's too long. 9 is too long. 6 plus 2 doesn't even reach the 9. And so that's what our triangle inequality is saying. The two smaller sides have to be bigger than the largest side for this thing to work. And so we're going to say no here. Since our two smaller sides, the sum is less than our largest side. Okay, and so we're using that triangle inequality theorem. We would need the two smaller sides to be greater than that third side. On part B, if we take the two smaller sides, 4 and 6, add them together, you get that's 10, which is larger than 9, and so we would say yes. By the triangle inequality theorem. So here we have 4 segments, lengths 4, 6, and 9. And by the triangle inequality theorem, we said they should be able to make a triangle. So let's see if we can do that. And you could see that we can roughly get that to work there. And so yeah, those 3 side lengths will work. Again, the smaller, if you add up the 2 smaller side lengths, they should add up to something larger than the largest side length. And if that's true, then you'll be able to make that triangle. Right, example 5. The lengths of 2 sides of a triangle are given. 18 and 23. Find the range of possible lengths for the third side. So there are 2 cases here. First, these 18 and 23 may be the smallest sides. And so if 18 and 23 are the smallest sides, then we're going to add them up together. Actually, before we do anything, let's say our third side is x. Okay, x meters. So if 18 and 23 are smaller than x, then we would want 18 plus 23 to be larger than x. 18 plus 23 is 41. So x has got to be smaller than 41. That third side has to be smaller than 41. So that's the case when x is the largest side. Now let's say that x is not the largest size, or the largest side length. then the largest side length would be 23. And then we'd say, well, 18 plus x has got to be greater than 23. And so solving for x, we get x has got to be greater than 23 minus 18, which is 5. So this gives us the limits on the third side. X has got to be bigger than 5 and at the same time smaller than 41. To put that together as a compound inequality, we could say x is between 5 and 41. Greater than 5 and at the same time less than 41. Pick anything in between, 5.1, 40.9, 10, 21, all those would work for x, as long as it's between those two numbers. Let's go to part B. If our two side lengths were 20 and 35, and we're wondering what our third side length could be, well, if our third side length were the bigger of the three, we'd say 20 plus 35 needs to be bigger than x. So 55 is bigger than x, or x is less than 55. On the other hand, if x is not the largest of the three sides, then 35 would be, so we'd need 25 plus x to be greater than 35. So x would be greater than 15. So x needs to be greater than 15 and less than 55, or we can say x is between 15 and 55. Determine which segment is the shortest in each diagram. So here's our diagram. We have two triangles right next to each other. PQR is isosceles, and RQS is a right triangle. First, find our missing angles. So we know these two angles are the same. We'll call them X right now, because this is an isosceles triangle, and the isosceles triangle theorem tells us that the base angles of an isosceles triangle are equal. So, well, x plus 30 is 180. So 2x is equal to 150. So x is 75. So I'm going to erase those x's and put 75 in. In the right triangle, we have angle S plus 40 plus 90 is 180, and 40 plus 90 is 130. Subtract 130 and we get angle S is 50 degrees. And so now we know all the angles inside this figure. So which side length is the shortest? And the angles are going to help us with that. The smallest angle is 30 degrees out of all the angles. So does that mean that QR is the shortest length? Well, be careful there. If we go back to the theorem that we were looking at, we're given angles, so theorem 33, given angles, which one's larger than the other depends on which side length is larger than the other, and notice that's only talking about one triangle. It's not comparing two triangles together. And so that's what's happening here. We have two separate triangles, and so just because we have 30 degrees in one triangle, and that angle smaller than the 40 degrees in the other triangle, that we're dealing with smaller sides. Let me so here I have two triangles, and I've measured their side lengths and I've measured their angles, and so I'm going to arrange it so angle C is the smallest angle, but you can see the opposite side to angle C is 5.77, and that's not the smallest side length. The smallest side length is the 3.75, which is opposite a 40-degree angle. And the reason that happens is they're in separate triangles, and so we just got to work with that. What we can do here, let me just, so in the triangle on the left-hand side, the smallest angle is 29.54, and so we can say that 5.77 is the smallest side length on the triangle on the left-hand side. And then if we look separately at the triangle on the right-hand side, the smallest angle there is our 40.38 right here. And so the smallest side length of that triangle is going to be the 3.75. Now, the smaller triangle shares a side length. Side AB is shared between the two triangles. Right? And because it's shared, and it's not the smallest side length in the smaller triangle, and so it's pretty obvious that 3.75 is the smallest, but we're going to have to use some of this logic when we don't know any of the side lengths. So let's get to the example that we're looking at here. Here we know the angles, but we don't know the side lengths. And so we need to know which segment's shortest, and we need some logic pointing to why it's the shortest side. So on the triangle on the left-hand side, angle P is the smallest, and so QR is the smallest side in triangle QPR. So I'm going to state that. So QR is the smallest side in triangle PQR. So separate the triangles first. Then look at the second triangle. In the second triangle, the smallest angle is 40 degrees, so the shortest side is RS. So RS is the shortest side, or the smallest side, in triangle QRS. So which one's smaller, QR or QS? Is there a way we can compare them? Well, QR is in both triangles. If we just continue to focus in on the smaller triangle, QS is the smallest triangle, the smallest side in triangle QRS. What can we say about QR? QR it's not the largest side, it's opposite 50 degrees, so QR is greater than RS in triangle QRS, since the angles opposite them in that one triangle, so we're only looking at the triangle on the right hand side, since 50 degrees is greater than 40 degrees. And so that's our comparison. When we're looking at which one's bigger, QR or S, we just look at the triangle on the right hand side, because that triangle has both of them in it, and then that establishes, okay, we know QR is greater than RS, so out of our whole diagram, RS has got to be the smallest side. And that's the end.